Mike Bernhardt for the Exascale Computing Project. I've got the privilege once again of coming to you from Argonne National Laboratory. Today we're meeting with Franck Cappello. Frank's a senior computer scientist at Argonne National Lab, and he's an adjunct research professor at the University of Illinois at Urbana-Champaign. But he's got a lot of other roles. You know, Franck is the ECP's principal investigator for a project we call EZ, and another project called VeloC, which has to do with checkpointing for large files. And he's also the data reduction lead for CODAR, one of our co-design centers. But Franck, welcome to the program.
Good afternoon.
And today what we'd like to focus on is your project called EZ.
Yes.
Now,
okay.
as I understand EZ, it's about compression software, preparing for a future set of exascale applications.
Yes.
We have a lot more followers. I know we've done a program with you in the past, but since then, a lot more followers have been paying attention to the Exascale Computing Project. So I'd like to ask you to go back and give us another overview. Like, what was the motivation for this project called EZ?
So the EZ project motivation is really to address the need for some of the ECP application to reduce the data set that they are producing. So if you look at the current simulations or the current instruments, they are already generating a lot of data, in fact too much data, and they cannot store or analyze or transfer all that data. Mm-hmm. Right? So they need to reduce the data, and there are different ways of doing that. One is to try to use what we call lossless compression. So it's a data reduction technique that doesn't lose any information. Right? You don't introduce any noise.
All the information is intact.
The information is intact. Mm-hmm. The problem with that is that we are dealing in scientific computing with floating points values, and these values are very difficult to compress. Sure. And the best we can do with lossless compression is typically a reduction of a factor of 2. Mm-hmm. These applications in ECP, they are looking at reduction factor of 10, 30, even more, right? So this cannot solve the problem. There are already some Lossy compressor in the literature as software, but one of the difficulty with this Lossy compressor, the existing ones, is that they cannot compress very well 1D data set or two-dimensional data sets, right? So data set that do not use a lot of dimensions. And so the EZ project is really targeting that type of data set, and also targeting data sets that are with higher dimension. In some cases, EZ provides better compression than the other existing data set for these very large, highly dimensional data sets.
Okay. So we have a lossless, you mentioned, which is just really not compression for the most part.
Well, you still reduce the data, but by half. Okay.
By about half. Okay.
But that doesn't solve the problem, right? What we really need to do is to get at least one order of magnitude.
Okay. So that's where Lossy comes in.
That's where Lossy needs to come into play, because you cannot do that without losing information. So one of the critical points here is that it's okay to lose information, but this needs to be very well controlled by the user. Right? The user needs to be able to set a limit for the accuracy. So you should not go lower than this accuracy level, right? So this is very important for the Lossy compressors to provide this control of the accuracy, and the user needs to understand exactly what it means for his application. And so we do that for EZ and the SD compressor.
Now, are we really only talking about image files?
No, in fact, that's maybe one of the, not mistake, but misunderstanding, let's say,
yeah.
right? So these applications, they are generating a lot of informations that will be processed and analyzed, but visualization is just one part of it. There is a lot of analysis done differently on these data sets, and image is just one case of that. And so I think we will talk about that later when we will discuss about the use cases. Okay. And you will see that, in fact, we have more use cases than we thought at the beginning. And visualization is just one of them, and there are a lot of others.
So is the primary technical motivation here a saving on memory and storage, or is it about bandwidth?
So if you are interested in the use cases, yes, there are. In addition to visualization, there are 4 other use cases that we can link to some ECP applications. So the first one is really to reduce the footprint on the storage system. So if you have your file system, you want to reduce as much as possible your footprint on the file system, then you will try to use lossy compression. And so we have seen that for the hack application, which is a cosmology application in ECP. And it's the case that they are generating a lot of data. They would exhaust the capacity of the file system, for example, of the system that we have at Argonne here, if they generated all the data that they produce during the simulation. And so they need to use data reduction technique, and compression is certainly one good direction for that.
Right.
So that's what's one thing. So for another application, which is called NYX, still an ECP application, we have observed that in fact by reducing the size of the data produced by the application, you can reduce the I/O time. So when you perform an I/O, you just try to save the data on your file system, on your storage. Well, if you can get a reduction of this data by a factor of 10, well, you may expect that the I/O time will be reduced by a factor of 10, right? That's the goal. In fact, we have observed that in some regime, the gain is even higher than that. Just because, in fact, you are avoiding some congestion on the file system, congestion that have non-linear behaviors.
Yeah, okay.
Right, so that's the second use case in addition to visualization. There is another one that we can link to the NWChem application, which is lossy checkpointing. So that's a very interesting and intriguing domain, but this application is interested in using EZ for that purpose. And so the idea is really to compress the checkpoint that you will use to be able to restart the application if a failure occurs, right? So if you have a failure, you want to restart. But here, in that case, you will restart from what we call a lossy state, which means that the state of the execution that you save in fact is lossy, so it doesn't have all the information that it has before you checkpointed. And what's very interesting with this application, and we have observed that with other applications, is that you can restart from a lossy state, and you can still converge to the same result or similar result. And that's a very interesting direction for fault tolerance in general, but also for the application of lossy compression. So it saves time, again, in the I/O interface, so you can save times while you are doing the checkpoint to the storage system, right? So that's a very interesting direction. And I think the most striking use case that we have seen so far is the one that the games application, we can link to the games application. And what we did was to try to see if we can improve the performance of the application. So it's not the I/O, it's not checkpointing, it's not reducing the size on the file system. It's really trying to see if we can accelerate the application by using lossy compression. And so what happened in this application is that there is a lot of electron integrals, electron repulsion integrals that are recomputed at each iteration of this application, and they are recomputed because they cannot fit in memory, right? And so since they cannot fit in memory, one solution is to say, okay, let's compress them, right, and try to see if they could fit in memory.
Sure.
So then you will gain the time of recomputing them at each iteration, right? And so we managed to develop a new compression algorithm that was able to compress by a factor of 17 that's called Aries. And in fact, now they fit in memory, right? And we observed an acceleration that could be up to 2.5 for some scenarios on this application. And that's a very striking result because we were not expecting that. And in fact, we got the best paper at the IEEE cluster conference just 1 week ago for that very interesting result.
It's pretty phenomenal stuff when you think about it. And checkpoint restart files can be monsters.
Yeah.
But Wow, I had no idea that this was so diverse. So it already sounds, conversationally here, you've already kind of jumped into where my mind was going, and that's progress that you're making with the software and the algorithms for lossy compression. It sounds like it's quite a bit there.
Yeah, so I have to talk about different applications, the 4 applications.
Yeah.
And in fact, if you look at these applications, the type of compression mechanisms that will work best for them is not exactly the same. So we did also progress on the technology of lossy compressor by going into what we call a multi-algorithm compressor. So this means that instead of having a single algorithm for the lossy compressor, we choose dynamically during the compression, in fact, the pipeline of compression that will fit the best for this application. Right? So it's really morphing the compressor as we compress to adapt it to the data set that we are compressing. So that's a new thing in this technology, at least in the domain of scientific computing and compression for scientific computing.
So Frank, are these decisions the user, the application developer has to make at a certain time? These aren't done automatically in any way?
So that's what we try to do, is to remove the burden of configuration of these compressors from the users, because if you look at even the JPEG 2000 compressor, for example, there's a lot of parameters in this configuration possibility. So that's your compressor that we use probably in these videos. For lossy compression of scientific data, and for some compressor, you also have parameters, and you want to remove as much as possible the need for the user to understand each of these parameters and control them very carefully. So one way to do that is to make that automatic. And to do that automatic, the best way to do that is to analyze the data set while you are doing the compression. So that's what we do. Wow. So when you are starting the compression, in fact, the first stage will perform some analytics on the data set to try to discover what are the features of this data set that could be exploited, to be able to compress the data set as much as possible.
Is there a connection here with machine learning?
So, in fact, that's very interesting. One of the problems with machine learning or deep learning is the complexity and the time that will be required to train, for example, an algorithm for that. Compression is a very difficult problem, because you need to compress very strongly a data set, reduce its size very strongly, but also keep the accuracy very high, because the user wants to get his scientific result at the end. And also it needs to be super fast, because if it's not super fast, then the user will not use it, because it will slow down his execution. If it needs to be super fast, then this limits drastically the type of techniques that you can use, and deep learning so far seems to be too slow to be integrated into fast lossy compressors.
Okay, that makes sense. Talk to me some more about usage diversification. The term gets tossed around, but I'm not sure a lot of the folks that are following this area, or starting to follow this area, really understand what you're talking about there.
Well, so it was just these 4 types of new usage that I just mentioned at the beginning. It's really, we were not expecting that during when we started the ECP project, and it's really during the ECP project and with the discussion of the application that we discovered that there are different usages, and these are different needs. For example, when you want to restart from lossy checkpoint, the accuracy that you need to be able to converge afterwards is higher than the accuracy that you will need for visualization, for example. So you may need different techniques to be able to fulfill these different requirements.
These are understandings that have come about as the project has progressed.
Yes, and with a lot of discussion with the application people. I think this is really co-design, in the sense that we cannot improve the compression technology without discussing with the application people and getting their feedback.
So tell me about the benefit or the value, if you will, of doing this as a part of the Exascale Computing Project.
Well, so of course, if we don't develop a new lossy compression algorithm for this application, then there is the risk for them to, for this application, in fact, to rely on some low-quality data reduction techniques. So one of the techniques that is used is called decimation, and it's essentially you remove data. For example, if you have 10 snapshots, or during your execution you save iteration data, well, you just remove some of the iteration data and you try to recompute them using some form of interpolation. So that's called the time decimation. You can also do that in space, removing data by using some sampling and then trying to reconstruct that using some form of interpolation. But if you do that, the quality compared to lossy compression is really lower, much lower. And so you cannot do the same thing with this technique that you would do with lossy compression. So really providing lossy compression will help the application, the ECP application, to address their need in terms of data reduction.
And how do you deal with error assessment?
Yeah, so that's I would say, one of the main topic here. When we start discussing with the application people, immediately what comes into the discussion is the notion of error. Okay, so your lossy compressor will introduce a noise, will introduce some error. How does this affect my data set, and how can I be sure that in fact the result is still okay, right? Yeah. And so for that we are trying to improve the methodology by developing a set of metrics. So that's what we do in the context of the CODAR co-design project, is really to, with a team of mathematicians and statisticians and with the application people and also developer of lossy compressor, try to list the type of metrics that the user will be confident to use to assess the quality of the lossy compression. Right? And that's a first step, is list from what's available, the metrics that are available, the ones that are relevant. But I think we need to go beyond this point. We need to design new metrics, and that's what we are trying to do now, that really extract from what the people are doing with their data set, extract the very substance of what's behind, right? So you may need to have a characterization of error which is specific to your application, right? But maybe different applications may have some common element behind them, and that's this common element that we are trying to find. So that's for the metrics aspect, and that's the science aspect of it. But then you have also a user aspect of it. You need to provide tools, right? A user will need a tool to be able to assess this error. And so we have developed, again, in the CODAR ECP project, a tool which is called Z-Checker. And that's a community tool, so people can contribute if they want. And this tool essentially takes two data sets as input, the initial data set and decompressed data set, right? And it computes the error with many metrics. So it shows you the nature of the error that exists between these two data sets. And that's a very important point for the acceptance of that error for the users, right? The user needs to be convinced that this error is not disturbing the results.
Of course.
Yes, and we do a lot of analysis, like autocorrelation of the error itself, also spectral analysis, and a lot of analysis on that. But again, the metrics themselves are not completely stabilized, so we are continuing to work on that and identify the right metrics for these applications.
Okay. So I'm new to this. I'm a novice at it. I'm just trying to piece all of this together. So I have a file, and I run lossy compression on it, and I now have a compressed file, but some pieces are missing. And the software has figured out how to handle that, and the user understands that I still have data that's good enough to work with. If I take that file later, and do I run lossy compression on it again if that file, as I add to it, continues to grow? And if I do that, now there's more missing, does the file start to degrade over time?
So yeah, that's a question that we have often, is that you compress once, you get something, and you compress more. Right?
Yeah.
And so in fact, you have to understand that what we compress is floating point data, right? That's what we compress. So you have, let's say, a string of floating point data, and that's what we compress. At the end, if you can compress by a factor of 100, let's say, well, we do that for some data file.
Yeah.
But this means that each floating point data is represented in this compressed format by less than 1 bit. So you cannot compute on that. You cannot do anything on that, right? So, and you cannot use the lossy compressor again on that because this is not floating point data, right? So you may try to use lossless compressor like JZip or Z-standard, and sometime you will get 10% improvement, but that's if you are lucky, in fact. So there is no real benefit of doing that. But that's the situation. No, you will not get higher compression level by applying multiple times the same lossy compressor.
Got it. Okay.
Yeah.
So it sounds like you're very excited and you're upbeat about where things are. You've made a lot of progress.
Thank you.
Algorithms are coming along. First Exascale platform scheduled to be out here, right down that way.
Yeah.
In the near future, not too far from now. Think you'll be ready?
Yeah, we are very motivated, and the results that we got so far are very encouraging, and so I think, yeah, we will be ready, yes.
Are you're using systems like Theta and so forth? How are you testing it today?
Yes, we test on Theta, we test on other systems, the system that we can use. One of the problems that we have is that we need very large disk space because we are working with very large data set to be able to compress that and to be representative of what we will have at Exascale. So we need to find platforms where we have enough space to run our experiments.
Okay, great. Is there anything else that you'd like to tell the audience about EZ and the compression that you're working on?
Yeah, so I think I would like to finish with one point, which is that we would like to encourage, in fact, the community to join this effort, and we have opened in July a website which is called Scientific Data Reduction Benchmark, so SDR Bench, and you can find that on the web. And what's interesting in there is that the community will find data sets from ECP and from other places that people can use to try to develop new compression techniques, right? Yeah. And they will find also the metrics that they should use to be able to assess that, and they will find also a link to Z-checker what they can use to assess the quality of their data reduction technique. So I think it's interesting because it will increase our possibility to design new algorithm, and I hope that students, for example, will be interested in doing that.
Well, we'll certainly point the community to your website pages and your project pages, and see what we can do to raise awareness for the project as well.
Thank you. Thank you.
Thank you. This is a great update, Frank.
Thank you. Thank you very much.
My pleasure. Yeah. All right, we've been speaking with Franck Cappello at Argonne National Laboratory. For the Exascale Computing Project, I'm Mike Bernhardt.